Hi there, Chase Gutierrez here from Positioning Universal. Have you ever wondered how car devices communicate with each other? Like, how does me switching the gear to reverse automatically turn on the backup camera on my dashboard screen? The screen has to be connected to the gear, right? But wait, does that mean all of the devices in the car are connected? There can be 80 plus devices called electronic control units, or ECUs, in a car. So that would be a lot of connections. I know I wouldn't want to wire all of that. However, there is a method to the madness. The CAN bus allows ECUs to communicate efficiently and without all the complex wiring. The CAN bus creates a centralized communication network, and even with 5 ECUs, you can see the difference. Now, how does this work? What if multiple ECUs send a message at the same time? Let's dive into this a little deeper. In a CAN bus network, there exist 2 lines that complete the network, CAN high and CAN low. These are bookended by resistors to prevent data from being reflected from the lines and echoed back, which would cause interference. Each ECU has 3 parts that play roles in the CAN bus. There is the CAN controller, the CAN transceiver, and the CAN node, which is the microcomputer inside of the ECU. In a functioning CAN bus, these 3 interact based on whether they receive or send a message in the network. So let's start with the example of an ECU sending a message to the network. First, the CAN node or microcomputer would send the transfer data to the CAN controller. From there, the CAN controller sends the data to the CAN transceiver. After that, the CAN transceiver processes that data and converts it to electrical signals that then get sent out into the CAN bus data lines. Now, we'll say an ECU receives a message. So in this case, the CAN transceiver receives the message from the CAN bus data lines. The CAN transceiver converts the data and sends it to the CAN controller. And then the CAN controller receives data from the transceiver, processes it, and relays the data to the CAN node. The CAN node now checks to see if the data received is important for their functions or not. If the data is important, the data is accepted and processed. However, if it's not important, the data is just ignored. Each CAN bus message in the CAN network is called a CAN frame. These frames can either be broadcast to all the ECUs in the network, or they can be directed to a specific ECU. The standard CAN frame has an 8-field format. These fields include the startup frame, the message ID, the remote transmission request, the control, the data, the cyclic redundancy check, the acknowledge field or confirmation field, and finally the end of frame. So going from left to right, the start of frame signals the beginning of a frame with a dominant 0 bit versus the recessive 1 bit state. The message ID defines the priority of the message based on which CAN node is delivering the frame. The lower the number, the higher the priority. Standard arbitration IDs are 11 bits and extended arbitration IDs are 29 bits. The ID is based on the node and not the actual message being delivered. So in other words, lower priority CAN nodes must wait for openings to transmit their messages regardless of the message. The remote transmission request field is part of the arbitration process and lets you know whether or not the data being sent is directed to one ECU or is available for all of the ECUs. The control consists of 6 bits. It includes the data length code, which is 4 bits, and 2 bits reserved for future expansion. These bits show how items of data are being sent in the frame, and it basically allows receiving nodes to verify whether or not they have received all the information that was sent. Next up, we have the data, which, as said, contains the data being transferred, and this can be anywhere from 0 to 64 bits. Now we move on to the cyclic redundancy check. This field is just to make sure that there are no transfer faults and is also called the safety field. The acknowledge field or confirmation field sends a signal to the transmitting node, basically acknowledging that the message was received. Likewise, if an error is detected, the transmitter is notified of the error and resends the data. Finally, we have the end of frame, which marks the end of the CAN frame. As mentioned earlier, a vehicle can contain 80 ECUs. Now, while the CAN bus network is much more efficient than connecting via point-to-point connections, with 80 ECUs, the CAN bus can be overloaded and cause a lot of data backup because of the way these ECUs communicate, which is based on a priority system that we discussed earlier. To mitigate this problem, there are actually several CAN bus networks which are grouped by priority and function. These groups can include the powertrain, body, comfort, and many more. And also these subnetworks can be connected by a gateway that allows for communication between each CAN bus if necessary. Now looking at these subnetworks, they operate on different speeds. These speeds could be high, medium, or low, and that is based on the priority of the data and their functions. So for example, the CAN bus network controlling the engine data would be on a very high priority and thus would have high speed. However, the CAN bus controlling the entertainment system is going to operate on low speed because it is much less critical. And the reason why they are not all high speed is because high-speed CAN bus networks are much more expensive. So creating these lower speed networks actually can cut costs while maintaining the same performance. This centralized CAN bus system allows for easy implementation of external telematics devices such as Positioning Universal's FT7500. The FT7500 syncs to the vehicle through simple, seamless installation and then can read data from all of the ECUs present in the vehicle. From there, the FT7500 reads the Vehicle Identification Number, or VIN, and sends it to the cloud where it is parsed. After that, a file is returned from the cloud to the FT7500 that then allows the device to read custom parameters from that specific vehicle. This allows for exceptional customization of monitoring from vehicle to vehicle, really optimizing fleet management. In conclusion, the CAN bus network creates a much more centralized and efficient method for devices to communicate from one another. By creating this centralized method, devices like the FT7500 and its paired AI fleet camera solution can access critical data that tremendously improves fleet management and, more importantly, fleet safety. Now be sure to subscribe to our channel so that you can catch our next edition where we detail the specifics of edge processing and just exactly how that works in relation to video telematics. Thank you.